We're going to continue talking about electrochem today, focusing on electron transfer fitting into big idea 3. Last time we talked about calculating cell potentials when we have a galvanic cell, and one of the things that you saw is when you calculate the cell potential, it will be positive. When you have a galvanic or voltaic cell, you will have a thermodynamically favorable reaction. If you have a thermodynamically favorable reaction, is delta G positive or negative? Negative. Keep that in mind. We are going to link electrode potentials, that is cell potentials, spontaneous change, or I guess we should say thermodynamic favorability, and equilibrium. So let's change this to thermodynamic favorability, as the AP exam has moved in this terminology rather than spontaneous, and equilibrium. So we're going to link several concepts together. And this is one of the things you'll be doing over spring break, trying to link concepts together that we've talked about this year. When a reaction occurs in a voltaic or galvanic cell, those terms are synonymous. It does perform work, and you can calculate that electrical work by multiplying N, the number of moles of electrons. I'll show you how to determine that. Faraday's constant, which is 96,485 coulombs per mole. That's what's given to you on the back. I was going to say the back of your periodic table, but it's really your reference sheets. You can simplify it to this, or honestly, in many cases, in a multiple choice situation, I'll use 1 times 10 to the 5 just for simple multiplication skills. And that will be coulombs per 1 mole of electron. E cell is the cell potential, that's in volts, and electrical work is coulombs, volts, or joules, and you'll see the cancellation of units as we work through. Now, electrical work is related to free energy, and we say that the maximum amount of electrical work is equal to the negative delta G, and you don't really need to be able to flip between those two in any regard. What you are going to see is for a redox reaction, delta G, that's the change in Gibbs free energy, is equal to negative, because of that sign right there, N, number of moles of electrons, F, Faraday's constant, E cell. And for number of moles of electrons, for example, if you have a redox reaction and when you balance it and get the number of electrons to be the same, that total number of electrons transferred is equal to N. And I'll point that out as we go rather than writing a fresh equation. If you have conditions at electrodes that are not standard, that is, you don't have 1 molar concentration, or perhaps you do not have 1 atmosphere of pressure, you won't have the little naught sign. But under standard conditions where the concentration of a solution is 1 molar or the pressure of a gas is 1 atmosphere, then you can use standard conditions shown here. And this formula too is on the back of your periodic table or on your reference sheets. It will be a separate sheet in your exam booklet in May, and unfortunately it's not a sheet that you can pull out, and you find this mixed in with thermodynamics. So you have delta G is equal to delta H minus T delta S, the change in enthalpy minus the temperature in Kelvin and the change in entropy. Delta G, you've seen before, is also equal to negative RT ln of K, that is the equilibrium constant, and here's your link right here. Delta G is equal to negative NFE, And on the right side, again, the standard reduction potential shown here. We showed you how to calculate that the other day, cathode minus anode. Faraday's constant, coulombs per mole of electrons shown right here. And they also tell you that 1 joule is equal to 1 volt times 1 coulomb. So you have that conversion shown here, and n number of moles. So those designations are indicated on the back of your periodic table. As a reminder, for a reaction to be thermodynamically favorable, delta G will be negative. What combination of enthalpy and entropy will always give you a thermodynamically favorable reaction? When delta H is negative, exothermic, and delta S is positive because you have disorder. So an exothermic reaction that illustrates disorder is always, always, always thermodynamically favorable. So you've got to start to make these connections. If E cell is positive, which it will be for a voltaic or galvanic cell, the reaction in the forward direction is thermodynamically favorable. Delta G must be negative, and you can see that from the formula highlighted in yellow right here. So if E cell is positive, a negative times a positive is a negative. Delta G will be negative. The reaction, of course, will be thermodynamically favorable in the forward direction. When E cell is negative, the reaction in the forward direction is not thermodynamically favorable because delta G will be positive. Because if you put a negative right here, a negative times a negative is a positive. And sometimes that's the only interpretation you need, is off the formula without plugging and chugging away. When E cell is at 0, the system is in a state of equilibrium, because if E cell is 0, what's delta G? 0. Anything times 0 is 0. When you reverse the reaction, you're going to change the sign of both E cell and delta G. And let's take a look at the following problem, because this will review what we did the other day and add the new piece of the puzzle in. Several questions I'm going to ask here to make sure you understood what we did yesterday. We went through very, very slowly to make sure you understood certain pieces. Let's make sure you've got it. It says, is the following reaction thermodynamically favorable in the forward direction? How do you know that copper is oxidized?
Electrons are lost.
Electrons are lost. Good. Oxidation always occurs at the anode or the cathode? Anode. Anox. To calculate E cell, you do cathode minus anode. Now shown here, you've got a an oxidation reaction for the first, a reduction reaction for the second. So you're not showing the equation that you would be provided with on any type of table, because those are always reduction potentials. So this is oxidation, this is reduction. E cell is cathode minus anode. Even though I turn this equation around, I didn't change the standard reduction potential. So this is the standard reduction potential, even though the oxidation reaction is indicated there, the half reaction. Cathode minus anode gives rise to a positive E cell. If you have a positive E cell, how do you know delta G must be negative? And that could be your question. So if you have a positive E cell, why must delta G be negative? They do have an inverse relationship, but I would indicate it based on the equation shown. So based on this particular equation, when E cell is positive, which it will be for a voltaic or galvanic cell, a negative times a positive gives rise to a negative delta G. Thus, the reaction in the forward direction is thermodynamically favorable. All right, make sure you're clear there. And that's what I indicated to you in your notes. You also could be asked to calculate delta G. It says using the information above, calculate delta G. So again, your formula. The N is the total number of electrons transferred. So when you go back up here, you lost 2 in the oxidation reaction. You gained 2 in the reduction reaction. 2 electrons, 2 moles of electrons right there. Faraday's constant is provided to you. Sometimes I just round it, it's easier. Note the cancellation of moles of electrons there. And then the E cell we calculated right here, cathode minus anode. Multiply it off. It comes out in joules because coulombs times volt is equal to joules. If they ask for kilojoules, you can move the decimal 3 to the left or divide by 1,000, and you've got negative 88.8 joules. Here I was just watching my sig figs. For sig figs, that's going to go based off the voltage. Don't base it off the number of electrons. That is a whole number. That's not relevant for significant digits. All right, let's take a look here. Determine whether the following reactions are thermodynamically favorable under standard conditions. I'm going to work the first one with you. You're going to work the second. So what is provided here is a balanced equation that I am going to write down for you. You have 2 gold 3 ions reacting with 6 moles of iodide ion to generate 3 moles of iodine and 2 moles of gold. I am told that for these 2 reduction half reactions shown, the standard cell or the half cell potential here, the reduction potential is 1.50 for the first and 0.53 for the second. And I want to show you how you're approaching this type of problem so you know. Is this equation written in the direction consistent with that one? Is gold 3 ion a reactant here as it is here? Yes. So this is reduction, and reduction occurs at the cathode, red cat. Now the second equation is in the reverse order from what's illustrated here, correct? Okay. So that tells me that the equation I really need is the reverse one. And so this is oxidation at the anode. Do the electrons match? No, they don't. How many total electrons is transferred? Please don't say 5. What is the least common multiple of 2 and 3? 6. So N is 6 moles of electrons. You would have multiplied this one by 2. And for this one, you would have multiplied by 3. And now you're seeing where those come into play. And I dropped my little ion there, bad girl. all better. Now, even though I multiplied both of these equations off, these are intensive properties. I'm not going to multiply these. And even though I flipped the order of this, in order to calculate E cell, if you want to do cathode minus anode, do not change the sign. So my E cell is just 1.50 volts minus 0.53 volts, and that is 0.97 volts. Now the question is, determine whether the following reactions are thermodynamically favorable. So for this first reaction, why is it thermodynamically favorable?
Since the E cell is positive, it multiplies times the negative amount of moles and you get a negative number, and then the negative delta G is favorable.
Right, and it's not necessarily negative amount of moles, but you've got a negative in there, and you are correct. This redox reaction is thermodynamically favorable because a positive E cell introduced into delta G is equal to negative NFE will generate a negative delta G, which denotes or represents, or whatever word you want, thermodynamic favorability. In addition, if you have a voltaic cell, E cell will be positive, delta G must be negative for the reasons we discussed. And with voltaic cells, you do have reactions that run without any assistance. They are thermodynamically favorable. Electrochem is actually pretty easy. It's just something you really haven't played with much before other than balancing redox reactions, so that's the challenge there. It's just new. It's not something you really explored in honors. Same thing on this problem. See if you can get it to rip. Bless you. How'd we do? How'd we do? Yes, yes? Okay. Not so bad, right? And like I said, Electrochem, compared to what you've been through, is relatively straightforward. It's just new. There is a light, I promise. And you will see it on May the 7th. The other problem is equally as easy, but you've got to remember one key thing about voltaic cells. So in the next problem, it says a voltaic cell is set up using silver, and silver ion is 1/2 cell, and chromium 3 ion is the other 1/2 cell. The half cells contain equal volumes of solutions and are standard conditions. Write the balanced net ionic equation for the spontaneous cell reaction and calculate both E cell and delta G. So, all they're giving you are reduction reactions and reduction potentials. So you need to So you need to figure out which reaction you need to flip and why. The key phrase there is voltaic cell. If you have a voltaic cell, is E cell positive or negative? All right, make it work. Oh. And note it says the balanced net ionic. Do we have an answer? Not yet? You should be able to do the voltage in your head. How would we do? Yes, yes? Were you able to do it? All right, so you knew E cell had to be positive, and the only way you could get it to be positive is if you did cathode minus anode in this regard. That told you that the silver ion was being reduced to silver, chromium being oxidized to chromium 3 ion. Question: what metal represents the anode? Anode is where what occurs? Oxidation. So which reaction did we flip? The chromium one, right? So your anode is chromium metal, correct? And the electrode, in this case the anode, is a metal. No charge, no subscript, nothing silly. Which metal increases in mass? Or which electrode increases in mass? The silver, because that gets generated. Does that make sense? Okay. Also, if you had one cell in which you had silver, and we said this will be the cathode, and the other half cell in which we had chromium, let's pop that little salt bridge in. And let's say in the salt bridge I had potassium nitrate. Here we're generating chromium 3 ion. Here the silver ion is being utilized. If I looked at that salt bridge, potassium ions would be moving toward which half cell? All right, because you'll have some negative charge in here and you want to balance it, also replacing positive charge lost. Here you're generating positive charge, so the nitrate ion will move toward it, correct? Does that make sense? This was asked back in 2014. It was a bomb. All right, so there's your voltaic cell, and I think you have a pretty good basis. Key thing today is that voltaic cells are thermodynamically favorable with negative delta G's and positive E cells. The other thing I want to mention to you, and this actually puts some concepts together that you learned last year and this year. In regard to the activity series of metals, if you consider this, lithium is at the tippy top, gold is at the bottom. So lithium can displace potassium ion, sodium can displace magnesium ion, nickel can displace copper 2 ion, gold is not able to displace anything. So when I say that, for example, and bridge the gap between honors and AP, if you had, for example, lithium reacting with calcium chloride at the honors level, you were like, woohoo, this is simple, I can do this. Bam. But at the AP level, you learned, ooh, the anion is a spectator ion, I'm not interested in that. And what you were really seeing was this, and then balance. So at the AP level, here's your single replacement reaction, a net ionic balanced equation. At the honors level, you were here. So lithium can displace calcium ion, generating lithium ion and calcium. And what you see with these single replacement reactions is the activity series is the complete flip-flop of your standard reduction potential. So you're going to see here that lithium is at the very bottom. Lithium here is most likely to be oxidized. It is the most powerful metal in regard to single replacement. On the flip side of that, and again, you're getting into a gas here, but cobalt ion and cobalt 3 ion and gold 3 ion are most likely to be reduced. So it's the complete flip. The activity series is the flip of the standard reduction potential. So here, zinc lies below the standard hydrogen potential, and as a result, it can displace. Here it would be shown above hydrogen as a more active metal, where if copper can't displace hydrogen, you can see it below on the activity series. On the standard reduction potential, you'll see it lying above. And that's just one thing that helps make these two pieces fit together. And shown here, it says write the balanced net ionic equation for calcium reacting with nickel 3 chloride. Calculate E cell and delta G. And that's just more of what we've done already. So I guess it'd be good practice. Give it a shot. It says write the balanced net ionic equation, and I'm even telling you which one to flip around. And what'd you get? 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 Negative or positive? Hmm? Mm-hmm. Like that? Yes, yes? And one of the next things we want to be able to do is from this formula, we want to be able to link it to this formula and potentially calculate KEQ. Now for voltaic cells, E cell is positive, delta G is negative. If delta G is negative, KEQ must be greater than 1. Be careful, positive, negative, KEQ is always positive, but greater than 1. And we will be linking these together next time. Make sure you know voltaic cells have a positive E cell and a negative delta G, consistent with the fact that the chemical reaction generates electricity. Questions?